So I got an email this morning asking me to go over the week to 12 discussion board. Unfortunately, the week they're not listed by week for me; they're just listed by title. So I'm going to go back just a couple ones for the organic one discussion boards, and we can do it for organic too. But I'm guessing the one is actually for the basic reactions of alkenes. So you're given this 1-methyl cyclohexene, and you're asked to describe how the functional groups change if you have Br2, if you have H2O Br2, if you have O3 H2O followed by zinc, and then if you have this plus Br2. And originally when I did this discussion board, first semester I taught this course online, I made the mistake of asking students to name what these compounds were and realized like it's actually kind of like organic too where they do this. But more just do you understand these reactions. So I'll write out what the products are. You don't need to be able to really describe the stereochemistry or any of that for some of these, but you should be able to recognize a few of these. The first of this is halogenation. And what we're going to end up getting is the trans-bromine product. So trans 1,2-dibromo 1-methyl cyclohexane. And it asks you what functional groups other than methyl, methylene, and methine are present after you do this. So the answer here is the alkyl halide. So we eliminate the alkene, and we do so by creating an alkyl halide. Now, the reason why I say ignore the methyl, methylene, methine, you're going to get a methyl group, CH2. So it's mostly for those people that are real legalist about this, and they say, well, technically there's an alkyl group in there. Yeah, I know. What new functionalities have you added with these reactions? Now, for this one, we're going to get both the E and Z conformations of 2-bromo, 1-methyl cyclohexanol. So in this case, we get an alcohol functionality and an alkyl halide. Now, with this lambda Br2, this is going to be a reaction that shows up a lot more when we start looking, you start going to take organic 2. We still have the alkene present. So we get an alkyl halide. And some people didn't put it, I didn't really take out points for it, but you also still have the alkene when you do this reaction. So with these types of reactions, we actually get stabilization of the radicals that are formed on this position. So with this lambda, we're creating a free radical that's stabilized by resonance. And we'll actually get two positions, one substitution here on this carbon that's adjacent, and another substitution here. But in either case, we get an alkyl halide and alkene. The last one, a bit of a weird one, this is the ozonolysis reaction. So the ozonolysis reaction clips the double bonds. So I've got 1, 2, 3, 4, 5, 6, 7. So this is carbon 1, 1, 2, 3, 4, 5, 6, 7. So the second carbon had this double bond, this becomes an oxygen. The seventh carbon has a double bond, this becomes an oxygen. So we get a ketone functionality as well as an aldehyde functionality. So with the ozonolysis, we end up cutting this double bond and replacing both sides of the double bond with an oxygen. In this case, these happen to be connected, so when it unfolds, we get a ketone and an aldehyde. Again, you're not required to name these types of compounds at this point, so don't worry about it. The big thing here is recognizing what functional groups you part on these molecules after you cut them open. So those are really all the requests I made. I'm just going through the emails right now to make sure. Um, yeah, that looks like all the questions I've been asked. So I need to take a look at a few things online, and then, but I've got this chat menu up here in case you got any questions. What is halohydrin? I have not come across the notes yet, so it looks like an OH and a halogen at the same thing. Yes. So the halohydrin addition will bring back up the molecule here. So it's an obnoxious portmanteau. The halo here refers to a halogen, and then the hydrogen here refers to a hydroxide, specifically an alcohol. So when we say hydrogen, we're adding water to it. Now, the way this ends up working is we go through a carbocation intermediate. So we have the bromine. This attacks one of the bromine atoms, breaks the bond, and we end up with minus. And then this subsequently attacks a water molecule. And through series of reactions, we end up getting, they end up being trans. So I'm thinking what this is actually more of like an addition, but it's like it's a two bimolecular addition. But yeah, it's an OH and a halogen added to the same ring. They're added across a double bond. The oxygen always goes to the more substituted carbon, and the halogen always goes to the least substituted carbon. So, you know, just give me a minute. Everyone, homework quest for test 3. Question for sharing what I'm doing wrong, but I named it 2,3,2,3,3 trimethyl 1-butene. So let me take a look at homework. Test 3 or test 4? Because test 3 is a brominated alkane. Okay, the alkene obtained by dehydration of 2,3,3-trimethyl-2-butanol. Okay, so this is an acid catalyzed dehydration. Luckily, we're already on the most stable cation. Now, by Zaitsev's rule, As that says rule, we always eliminate by the carbon with most hydrogens, but in this case the one that's adjacent doesn't have it, so we're going to get elimination here. So what do we call this compound? We got 1, 2, 3, 4. So I do agree with the butene. 2, 3, 3 trimethyl. Yeah, I'd agree with that one. Unless it's some weird trick question. Yeah, you shouldn't get rearrangement. So when I did it, it accepted 2,3,3 trimethyl 1-butene. So I got the same answer you did, the 2,3,3, and it seems to be accepting it on my end. So I can show you the desktop really quick. 2,3,3 trimethyl 1-butene. It seems to think that's correct. I mean, my only guess is maybe you accidentally put the 2,2,3,3. So you did it correctly, you just happened to like slip the digit. But yeah, I get the 2,3,3 trimethyl. It works. Yeah, I mean, it makes you feel better. Your answer is correct. Yeah, I fear that's what it was, because the two, yeah, I can see that. Question 18, part 2. All right, so first part, in the acid catalyzed dehydration of 2-methyl-1-propanol, a carbocation would be formed if a hydride shift accompanied the cleavage of the carbon-carbon oxygen bond. So let's start with the molecule, just for people who can't even get that far. 2-methyl-propanol. Or sec-butanol. So in this case, we'll form a carbocation, and with the hydride shift, we'll get that is our first intermediate. And then what ion would be formed as a result? So that's the hydride shift in terms of a methyl shift. So hydride shift, we take the hydrogen, we scoot it over. So the hydrogen's up here. For the methyl shift, we take it and scoot it over, and we'd end up with 1, 2, 4. This carbocation. Now, hydride shifts are kinetically slower, so we'd expect that not to happen. On top of that, this takes us to a secondary carbocation, this takes us to a tertiary, so we expect the hydride to be the more likely scenario. So which do you think will predominate, a hydride shift or a methyl shift? The hydride shift here is going to predominate because you end up with a third-degree carbocation versus a second-degree. And also just kinetically, the methyl is bigger, so it moves a lot slower. So even if the methyl versus the hydride, since you like the methyl is more stable, you'd probably get a fair amount of that product, but you'd still be kinetically limited. Hydride shifts are easier. Kinetically, they're super simple. The big thing your book is going to emphasize, and they're correct to emphasize it, is that if you do the hydride shift, you end up with a tertiary carbocation versus a secondary with the methyl. But you can also get, there are other reasons why you would shift one versus the other. So let's say, we had a carbocation like this. So you've got the option of doing a hydride shift. So if you did the hydride shift, you would end up getting the tertiary carbocation. Or you could actually do, actually I've drawn it wrong. So if we start with the carbocation here, we do the hydride shift, we create a tertiary carbocation, but if we do what would be considered a methyl shift here, we'd get a 6-membered ring. And so since the 6-membered ring is more stable than the 5-membered ring, this would actually be the predominant effect. We'd see the 6-membered cyclohexane formed over this methyl cyclopentane. So yes, kinetics do play a role. And in fact, if you want to trap this product, you would just run this at low temperature, since the hydride shift is a lot easier to accomplish than this methyl shift. But there are reasons why the methyl shift would occur over the hydride shift, even in the case where you go from a tertiary to secondary. And this is usually what you see with like ring strains. If we want to make a 6-membered ring, or we can make a 6-membered ring, we're going to favor a methyl or methylene shift over something like a hydride shift. And if you're going for organic too, then we also talk about, we allude to it, but we don't really talk about it too much, is that also you can create like aromatic rings depending on where your carbocation is, and this can sometimes drive that as well. Question 19. So predict the product of the following reaction. So we have a methoxide, which is a large base, and DMSO, which is a nice apolar, low dielectric constant solvent. So what we expect for this reaction is to go through an E2 mechanism. So we're going to have our Cl here, and there is a reason why they're drawing it branched out like that. So our methoxide should attack the hydrogen, displace it, and give us the trans product. So let's see if I'm right. Yep. So first thing we get is the trans product. Again, we're going to go through an E2 mechanism here. Same reason that you would go through like an SN2 mechanism. If you had something like this, DMSO is a low dielectric constant solvent. It's also aprotic. So now they have, consider the stereochemistry. We have HA and HB. And it wants to know which one's going to get removed. So we're looking for the one what's called anti-periplanar. So anti-periplanar means that we have a plane defined by the solid line, so we're looking for one that's on the opposite side. How do you spell that stupid word? Anti-periplanar. And it's to the leaving group Cl, and since HB here is anti-periplanar, I'm going to say it's HB anti-periplanar. I think this is the one that had the issue. Oh, I'm sorry, I got them flipped. HA, HB. Yeah, so I'm sorry, I drew it wrong when I put it up here. It does have HA on the left. We want the one that's opposite the chlorine in terms of the wedges and the dashes, and that makes it HA being anti-periplanar, means it's basically trans to the chlorine, but also on the opposite side of the bond. Low relative to something like water. Big thing is that it's aprotic. Also, if you ever see anything like an alkoxide, alkoxides are generally going to go through that 2 mechanism because they're inherently aprotic and they're also pretty big. Yeah, the low here is like relative to water. And even then, I'm still not convinced that's really a thing because we're definitely going to run a reaction in organic 1 that's being done in water and it goes through an SN2 pathway. I question sometimes if that's actually true. Again, I question, like your book talks about it, but I question it. So why doesn't it attack the one that's on the same side as the chlorine versus the opposite side? This is kind of a weird argument that gets made. So let me get out my modeling kit. And I will agree with you, it's one of those things that doesn't make sense. From a chemistry standpoint. So let's say for whatever reason we've got this molecule. So this is our halogen, and this is this is the hydrogen we plan on eliminating. So if I draw it on the board, I'm going to draw it kind of tilted, but we've got my halogen and I've got my hydrogen both coming up. And the argument is that when we do this reaction, when we abstract the hydrogen, the lone pair will actually swing down through the plane of the bond. So it can only give electrons to whatever is anti to it. So if we looked at the Newman projection looking that way, we've got X, whatever our methyl group is, the hydrogen, and behind it, we've got the hydrogen of interest, their hydrogen going down, and the other methyl group going up. So this is the argument that I've seen made in books, is to say that when this bond is broken, the electrons actually have to swing down through the molecule. So if they're actually on opposite sides, so they're anti-periplanar, this will end up putting our hydrogen opposite whatever our leaving group is. And so when we break this bond and we form the lone pairs will swing through the bond and displace. So if we break this bond, the lone pairs will swing up through the bond and displace the X. So mechanistically, this is what is claimed. The reality is that the theory for Lewis theory is not complete enough to explain why this occurs. This is actually a really gross oversimplification of what's happening. There's a lot of molecular orbital movements going on, and my guess is the intermediate actually looks something like this. When you get rid of that hydrogen, you have 1.5 bonds above and below, where you have 0.75 bonds. I don't want to put it. Basically, you're going to go through a transition state that's not predicted by Lewis theory. So again, the explanation I've seen given in textbooks is to say that they have to be on opposite sides because those lone pairs swing through the bonds. And form a bond with the carbon that contains the leaving group, and that knocks it off. You are right to say, well, why can't they just both be on the same sides? You create a lone pair, this lone pair leans over and kicks this group off and makes a double bond. And the real answer to your question is that it's much more complicated than what's being drawn for organic chemistry. This is just a very oversimplified mechanism that glosses over a lot of details. So I'm not trying to dodge your question. It's just that there's probably like a nice like molecular orbital theory explanation for what goes on and why they have to be anti-periplanar. But Lewis theory itself cannot give you a good reason as to why. We just know from empirical studies that it has to be. Got time for maybe one more question. Yeah, you're welcome. And again, there's live streams for us this week. Feel free to reach out, send questions in advance. Thanks, Niall, for showing up, and I will see a lot of you tomorrow.